Namaste. Space has become an integral part of our culture. It was on the 4th of October 1957 that the first human-made Earth satellite, Sputnik 1, was launched. A decade later, on the 10th of October 1967, the Outer Space Treaty was signed. In recognition to these two events, the United Nations General Assembly in 1999 declared that the World Space Week will be held from the 4th to the 10th of October every year. Today, we have an eminent personality, Dr. V. Narayanan, to talk to us regarding the excitements in Indian space arena, past, present and future. Dr. V. Narayanan is a distinguished space scientist in apex grade and the director of the Liquid Propulsion Systems Center, one of the lead centers of ISRO. He is a renowned technologist who has made remarkable contributions in the past 40 years in various areas of space technology, including the recent Aditya L1 mission and the Chandrayaan missions. Welcome, sir.
Good evening, Ranju.
Sir, certain events in history warrant memorial celebrations. Our India recently had one such. So let's start with the success story of the Chandrayaan 3 mission. How excited were you during this momentous feat?
You all know the Chandrayaan 3 was a grand successful mission, and India is the first country we landed in the south pole of moon successfully, and we are the fourth nation to soft land on the moon surface. Really, as a person involved in multiple activities of Chandrayaan 3, it was a so excited moment for me. As the director of the Liquid Propulsion System Center, for this LVM3, M4 and Chandrayaan 3 mission, we have significantly contributed. And for the vehicle, launch vehicle, we have delivered two important propulsive stages, the L1 ton liquid stage and the C25 cryogenic upper stage. These are the two important stages delivered for the launch vehicle, along with something around 220 health monitoring sensors and a host of control components for the solid propulsion system. Now, coming to the satellite area, again we have delivered two crucial propulsion systems. One system is meant for taking the spacecraft from the earth orbit to moon. Another system is meant for the landing, soft landing on the moon. So, these are the four major systems, propulsive systems you have delivered. In addition to that, I have got multiple responsibilities. You know, the first and foremost for lifting the Chandrayaan 3 is done by the LVM3 vehicle. LVM3 vehicle is a vehicle with 642 tons lift-off mass and 43.5 meter height. It has got three major propulsive systems. There are two solid propulsion motors, we call it as strap-on motors, of each having 207 tons of propellant loading, and there is a core liquid stage called L1 ton stage having almost 115 tons of propellant loading, and the indigenously developed the cryogenic upper stage having something around 28.5 tons of propellant loading. Now, the responsibility of the vehicle is to lift the spacecraft from the earth, and it has to give you a velocity of something around 37,000 km per hour for injecting in the predefined elliptical orbit of 170 km by 36,500 km. In fact, the dispersion defined for the elliptical orbit is 36,500 plus minus 500 kilometers, but it precisely injected with a very small dispersion of something around 9.5 kilometers from the required area. Now, to realize the vehicle, in fact, we have to realize the vehicle in a fast track mode to meet the launch requirement. As the chairperson of the Project Management Council of the Space Transportation System and also the chairperson of the LPSC and IPRC Coordination Committee, we had reviewed and I have put it in a fast track mode, and the vehicle was realized in a very fast track mode. This is one aspect with respect to the vehicle. Now, coming to once it reaches the elliptical orbit Now, next responsibility is we have to take from the earth orbit to the moon's orbit by traveling almost 3,70,000 kilometers. Now, this is done, rather this is accomplished by carrying out multiple maneuvers of the propulsive system which was in the propulsive module. In fact, you all may be knowing the 3900 kg Chandrayaan 3 spacecraft has got three major parts. One is the propulsive module meant for taking from the earth orbit to moon's orbit and getting it captured. Second thing is a lander system which had to soft land on the moon. Third is a rover. Now, the propulsion system in the propulsive module has taken successfully by operating the engine and thrusters almost 13 times and firing the system 10,000 approximately 10,300 seconds, and it has taken to the moon's orbit. Successfully it was captured in the moon's orbit. Then the orbit size was reduced to a level of something around 163 by 155 kilometer. It was reduced, and then the propulsion module was separated from the lander. After the lander and rover system got separated, again the orbit size was reduced. In fact, we carried out two deboost orbiting. Deboost means basically reducing the size of the orbit, and we brought to nearly something around 150 kilometer, that type of orbit. Then on the day of landing, soft landing, that was on 23 August 2023, it was a historical day. The lander and rover was rotating with a velocity of something around 6077 kilometer per hour, which is almost 8 times of the aircraft speed, and it was at the altitude of something around 31 kilometers. From that place, in a period of 19 minutes, we had to break the velocity, rather reduce the velocity, and we have to bring it in a predefined path, operating the propulsive system and multiple sensors, including inertial systems, which is guiding, which is understanding the position and giving the direction, and there are camera systems. Finally, we have to make the velocity, both horizontal velocity and vertical velocity and altitude, to near zero. And after making the velocity to near zero, we have to understand the hazard aspect of the moon surface. For that, we had a camera. That camera, using that camera, the location is understood, and if any hazard is there, we have to change the path. But fortunately, when the camera was operated, it was in the right place, and we made the soft landing. And you know, Indians are credited for discovering zero.
Yes.
In the earlier past.
Yes.
Now, here we used to say in a very lighter vein, three parameters: the altitude, horizontal velocity and vertical velocity, simultaneously we have made to near zero, and we have soft landed on the moon south pole as the first country and made history. This is really a very, very exciting moment for the entire Indians, entire scientific community across the globe. I am not an exception, and I am also so much excited on this historical moment of South Pole landing and making Indian flag to fly higher above all the other nationals' flag.
So, some of the rare occasions where zeros are celebrated, isn't it, sir?
Yeah.
Okay, sir. You were also the chairman of the Failure Analysis Committee of Chandrayaan 2. So, how important were your findings in the success of Chandrayaan 3 mission?
2019, when we made the soft landing attempt of Chandrayaan 2, up to a level of 2.1 kilometer, things were going well.
Yes, sir.
Beyond 2.1 kilometer, as you know, we could not accomplish the soft landing. Rather, we lost the signal, and there was a setback. Rather, it was a hard landing. Immediately after that, an expert committee was constituted, not only to understand the reason for the setback, also to study the performance of each and every satellite system. Something around 28 satellite systems are there, and to study its performance and give necessary recommendations for improvement to have a successful Chandrayaan 3 mission. Also, we have to pinpoint exactly what is the reason for the setback. That area also we have to give the recommendations. So, in fact, it was a 9-member committee with me as the chairperson. It was a national level committee, and we spent almost 1 month time. We were rather given 1 month time, and the team was working 24/7. In fact, the average sleeping time was less than 3 to 4 hours for all the members during that 29-30 days. And we really meticulously gone through the entire performance data and studied the performance of all the systems, including the guidance and control, software related aspects, camera, the payload, the sensors, inertial systems, propulsion systems, structures, all the systems. Finally, we could pinpoint the reason for the setback. Also, we had given recommendations, more than 100 recommendations for improving the performance to have a 100% successful Chandrayaan 3 mission. And the important improvements what we recommended are, number one, we told the entire propulsion system has to be tested identical to the flight conditions. In the flight almost it has to work 19 minutes, and the performance has to, the thrust, initially there should be a thrust, and the thrust has to vary continuously, and before soft landing from 4 engines we have to switch over to 2 engines. So, what we recommended was the flight hardware should undergo a test equal to the flight profile test. So, this was one of the recommendation. Another one was we had to improve the propellant margin for the entire operation. Suppose if the propellant is like a touch and go, that is what happened in Chandrayaan 2, then there can be issues. So, we increased the propellant margin, almost 172 kg additional propellant was loaded compared to Chandrayaan 2 to Chandrayaan 3. Then third is we recommended to improve the guidance and control system, rather the logics, algorithms. So, we wanted to, we recommended to strengthen that portion. Then the entire this 19 minutes operation is carried out in the autonomous mode. Okay. So, we had a software worth about 1.5 lakh lines, and the method followed for development of the software, testing, validation, and testing for the extreme conditions, carrying out simulations, that area also we recommended to strengthen. Then another area is in Chandrayaan 2, we planned to soft land in an area where the area was identified 0.5 kilometer by 0.5 kilometer. But here in the Chandrayaan 2, we had a very good orbiter, on-orbiter camera with 30 centimeter resolution. Using that camera, lot of photographs were taken on the moon surface, and using that we defined a space of 4 kilometer by 2.4 kilometer as against 0.5 by 0.5 kilometer. That means any dispersion we will be in a position to land in the appropriate place. This was yet another recommendation. Again, when you come from 6077 kilometer per hour and bringing the velocity to near zero velocity, we should accurately measure what is the type of velocities. So, there were additional sensors which were required. Then while soft landing, even if the velocity is little different than the requirement, we should not have a problem. So, you would have seen the configuration, there are like a 4 lugs, we call it as lander lugs. That capability, energy absorbing capability was almost increased. Rather, in Chandrayaan 2, up to 2 meter per second velocity only it can withstand, but here we strengthened and improved its capability almost 50% more. Okay. Up to 3 meter per second it can withstand, but what we achieved was less than 1 meter per second we achieved, and we landed, but that strengthening was done. Then thereby the cameras and its logics also lot of improvements were done. So, with all these improvements, and important thing is, after making the spacecraft, after integrating entire thing, we recommended to carry out extensive testing, because in the real environment the sensors, everything has to face. For example, when the engine is firing, how the cameras are working, when the engine is firing, how the inertial system is going to work. And this type of integrated test, there are 2 types of integrated tests were recommended. One was called the cold test. Cold test means simply take the system, for example, we are having altimeter, this type of thing, take by helicopter and try to understand how its performance. Another thing is called integrated hot test, and we integrate the entire thing, cameras, inertial system, everything, and fire the engines, and under that environment how the systems are working. So, this type of tests were carried out, and we have got lot of takeaways and we have strengthened. Thereby, I will say we have overseen all the recommendations are properly implemented, and all the tests whatever you have carried out, whatever strengthening we have to do based on the test data, that is also done. With that, we have gone ahead with the flight, and today it is history. We have got the successful landing on the South Pole, and successful landing. We were, even though we prescribed 4 kilometer by 2.4 kilometer, we landed precisely close to the required place, hardly 370 meter away from the nominal spot. So, that is the type of precision at which it has landed.
So, what are the benefits that Chandrayaan-3 offers to your country?
Now, these benefits of the Chandrayaan-3 I will split into 2 categories. One is a scientific related benefit, another one is a total, the country, what type of advantage it has brought out. Now, by the soft landing on the South Pole, and India is the first country which has soft landed, that has really brought glory to the country. Second major advantage is irrespective of the region, religion and the type of people, we have integrated 140 crore Indians across the globe through this Chandrayaan-3 mission.
Yes.
Third thing is, by successful mission, we have brought scientific temper in this country, not only with the educated people, even with ordinary citizens we could bring scientific temper. Third thing is, we have brought lot of scientific rather discovery, and these scientific discoveries were really rolled out to the scientific community across the globe. Thereby, the stature of the India is brought up, and we have contributed for the scientific community through these scientific discoveries. Another very, very important thing is, by this success, I consider, 1947 we got independence and our country was not a developed country that time. You take from that time to now, we have grown in all the areas, let it be agriculture sector, let it be health sector, let it be transportation, let it be infrastructure area, everywhere we have grown, and space program of course we have grown. And slowly 2047 I expect the country to become a developed country status, and this is a stepping stone towards that great success. And next important thing is, in the Chandrayaan-3 we had 6 major scientific payloads, and I am happy to inform that all the 6 scientific payloads have perfectly worked, and it has added lot of scientific data. And if you take the scientific data, for example, we wanted to understand the plasma on the surface of the moon, and we have discovered in 1 meter cube volume 5 million to 30 million electron content. This is one of the discovery. Another thing is, we wanted to understand the thermal profile of the surface, and for that we had a beautiful instrument with 10 temperature sensors, and this instrument was pierced inside the surface of the moon 10 centimeter, and we have discovered on the surface of the moon the temperature is 60 degrees centigrade, and in 10 centimeter down it is minus 10 degrees centigrade, and this data we have published. Another thing is, we wanted to understand the seismic activity on the moon surface. For that we had a payload with 6 vibration sensors, and when the rover was going out, we are clearly understanding some places are prone to seismic activities and clear data is available. And another important thing is, we wanted to understand the chemical and mineralogy available there, and we have discovered 6 minerals including iron, titanium, manganese, chromium, sulfur, oxygen, like that 6 minerals we have discovered. And in fact, I wanted to understand how accurate it is. You know what we do, we are having an instrument and there is a plate in which the really actual chromium or all these minerals are kept, and this sensor first faces that, understand what is the type of signal, and same thing it is taking on the surface of the moon, and when the signal is matching we declare. That means whatever we have declared is a very very accurate data. Yes. Another thing is we are having a payload on the propulsion system, which is trying to understand the spectroscopic aspect of the earth, and this is beautifully it is working, and using this surely in future it will add value to understand the exoplanets and other things, it will add value. Thereby the scientific discovery is really phenomenal, and ISRO as a organization and India as a country, we have declared all the discoveries to the world scientific community, and thereby today really it has brought huge value addition and huge benefit to our nation, and our national flag is really flying high.
Okay, sir. Then coming to Aditya mission, as far as Aditya L1 mission was concerned, you had multiple roles to play. First as a director of LPSC, then as a chairman of the MRR, Mission Readiness Review Forum, then also as a chair of PMC STS, Project Management Council Space Transportation System, and also as a chairman of ILCC. So these were the multiple roles which you had to play during this Aditya mission. So could you share your experiences during this PSLV C-57 Aditya mission?
No, Aditya L1 is a very excellent satellite. It is a satellite with 1480 kg mass with 7 important scientific payloads, and over 8 years our scientists and the ISRO community has realized that excellent satellite. And to this Aditya L1 has to be placed in a place between the earth to sun almost 15 lakh kilometers, which is 1% of the distance from the earth to sun area, and it has to go there, and there is a point called Lagrangian point. Yes. Where it is stable. Stably it can be placed, and it can rotate, and continuously 24/7 it can face the sun and do the research about the sun. So that is what about the satellite. Now again, to take the satellite, we used our PSLV C-57 launch vehicle, which is the 59th vehicle of PSLV and 57th successful PSLV vehicle, and this vehicle gave something around 34,000 km/h velocity and injected into a orbit of 235 km by 19,500 km we targeted, we got 19,520 km it injected. Now if you take the vehicle is a 4-stage vehicle, 2 liquid stages and 2 solid stages. 2 liquid stages, the second stage powered by the Vikas engine, we call it as the PS2 stage, and the 4th stage is powered by 2 pressure fed engines. So these 2 stages are designed, realized and delivered by the liquid propulsion community. In addition to that, there are 5 liquid propellant based control systems in this vehicle. So these things are delivered. Now if you take as a total vehicle, it is having something around 300 control components, dynamic control components are there with something around 200 sensors. So these things also for the vehicle, we as the liquid propulsion community, when I say liquid propulsion community, not only LPSC, because our IPRC, ISRO propulsion complex at Mahendragiri, they are also a partner with us in assembly, integration and testing. We together we have delivered these for the vehicle. So that is one of the major contribution. Then comes to the spacecraft. Spacecraft, as I told, it has got multiple systems. It has got power system, it has got structure, it has got onboard software, it has got inertial systems, and it has got again payloads, and it has got so many subsystems. And one of the crucial subsystem is the propulsive system.
Yes.
And there is a liquid apogee motor with this, there are 12 control thrusters and with something around 550 kg propellant loading, associated tank gauges, then pressure regulators, total propulsion system. This propulsion system is the one which is taking from the earth orbit to L1 point, traveling almost 15 lakh kilometers. This system is again realized by liquid propulsion team from LPSC Valiamala, LPSC Bangalore. I am having a unit in LPSC Bangalore. That unit along with IPRC team together we have developed, realized and delivered, and really beautifully it is working, and we have carried out 4 earth orbit maneuvers, thereby taking to almost 1,22,000 kilometer from 19,500 kilometer where the launch vehicle injected. From that it was taken to 1,22,000 kilometer. Then we operated the engine, and right now the spacecraft is moving towards the L1 point. Out of 15 lakh kilometers, right now we have reached approximately 10 lakh kilometers. But and the remaining place path we have to move, and we are expecting this to reach somewhere in January first week. That time frame we are expecting it to go to close to L1 place, and L1 again it has to be captured. After capturing it has to rotate in that place, and when it is when it is placed in L1, there will be small disturbances, and to take care of the disturbances we are having control thrusters. So, thereby it will be placed perfectly and facing the sun, and continuously it is going to do the experiment. Now, I had got other than, as you rightly told, other than the director of LPSC, the mission readiness review committee chairperson. The mission readiness review is the highest technical forum responsible for reviewing and clearing the launch vehicle, the PSLV rocket, the satellite, the ground segment, and all the associated range related equipments, everything. And in fact, it was a great experience as the chairperson of mission readiness review and the space transportation project management council. In that role, really we have to ensure the launch vehicle is realized in the right time, and it is really a very satisfying moment, because when you play multiple role, in multiple role you have to do multiple activities, and today I am happy that things are in order. And I want to tell the audience, we are going to be one among the 4th nation to have a satellite for studying the sun, and with the type of expertise, type of operation what you have done, I am 100% confident in January the satellite will go to the right place, and we are going to have a life of more than 5 years to study the sun, and we are going to add great values for the scientific community. And it will be a mission, exciting mission similar to the Chandrayaan-3 mission, yet another mission. It is a great challenge, and great excitement is going to happen in January.
Okay. From Aditya and Chandrayaan, let's now move on to another prestigious project of ISRO, that is Gaganyaan, sir. So, what is the current status of Gaganyaan?
No, Gaganyaan is a project you all may be knowing, meant for taking our Indians using our own launch vehicle to the Earth's orbit, low Earth orbit. And taking is very easy, but you have to take them and then keep them in the space very safely, and we have to bring them back. So, this is the basic objective of the Gaganyaan project. Now, it involves lot of developments. Number one, we have earmarked, rather identified the LVM-3 vehicle as the vehicle for this purpose, and the same vehicle as such cannot be used, and we have to do the human rating of the vehicle. When we talk about human rating of the vehicle, number one, all the systems, let it be propulsion system, avionics system or structure, everywhere we have to bring margin, we have to demonstrate margin. That is one aspect. Wherever margin was not there, we have, for example, take tank gauges, we have increased thickness wherever required, and we have built margin. Second thing is, we have to have redundancies. Wherever required, wherever possible, we have brought redundancies. Third thing is, we have to do so much testing and qualify.
Okay.
And for example, take C-25 propulsive stage, which is indigenous developed stage. We had defined, apart from whatever test we have done till now, 14 important hard tests we had to carry out in multiple hardware, 10 long duration tests and 4 off nominal tests. Off nominal tests in terms of thrust and mixture ratio, its operating condition, we have to perturb and understand everything is, rather validate everything is working. Similar case with the L110 stage. And today both the stages we have successfully completed the test program. Consecutively all the tests has gone well, and we have declared as it is a human rated L110 engine and C-25 engine. Now imagine when we have defined 14 tests, any test there is a setback, if you touch the hardware then entire test has to be repeated. And in fact, week before last week we had the major achievement of the last test of the C-25 engine. In the flight it is supposed to operate with a 20-ton thrust. So our test was take the thrust 10% more, 22 ton, and duration 560 seconds is the flight operation. So we put additional 25% margin. So we had to demonstrate, and that was the last test, and it was a so excited moment but a little tensed moment. Because any setback, entire 14 tests you have to repeat. But the type of professional work which has gone inside, the test was a very grand successful test, and we have completed. Similar case with solid motor. Solid motor also there are changes. For example, insulation thickness, we have modified the chamber pressure, operating chamber pressure we have reduced compared to the conventional solid motor, and we have brought some sealing redundancies, and thereby lot of improvements were done, and we have also carried out necessary ground test, and it is cleared. Same way, electronics packages, avionics system, we have brought quarterable redundancies, and the systems are undergoing final level of testing. So today if I say the vehicle per se is almost in the final phase, everything is completed. Now the second major development is the orbital module. Orbital module is the one where the human beings are going to be accommodated, rather they are going to be inside and they are going to be taken. And that has got so many systems. It has got a avionics system, it has got health monitoring sensors, then it has got the environmental control and safety systems. When the human beings inside, you have to ensure the right environment. For example, in terms of oxygen requirement, in terms of partial pressure requirements, in terms of humidity control, everything has to be controlled, and that type of system has to be developed. And when they are there, we call it as a pressurized cabin, and that development. And there are, if you take the orbital propulsion module, it consists of two parts. One is a service module, and where all gases, everything are kept, and another one is a crew module, where the crew is accommodated. And this has got, again, this is totally a new development. And in fact both are having two independent propulsive systems, because that launch vehicle places something around 170 kilometers. From there we have to take it to something around 400 kilometers. So there is a propulsion system, we call it as a service module propulsion system with 5 LAM engines. In fact, this Chandrayaan 3 and Aditya L1, for taking to the required orbit, we have used 1 LAM engine, but here there are going to be 5 440 Newton thrusters, we call it as LAM engine, 5 numbers of LAM engine plus associated control thrusters. So this is one of the systems. Like that, it has got n number of systems. Same way, the crew module is having another propulsion system, we call it as a crew module propulsion system for bringing them safe. And then there are host of parachutes for them to come back safely. And this system is a total new development. Currently the design is completed, hardware realization is going on. Now we are entering into a testing phase. Then the third important system is, we call it as a crew escape system, that is the topmost part of the rocketry. And that system is, when the crew is inside at different phases, for example when they are in the launch pad, due to some reason some setback happens, they have to be safely brought out. And when the launch vehicle lifts off, multiple phases, if anything happens to the rocket, there is a health monitoring system which will indicate, yes, the things are not under control, then immediately they have to be brought safely. For that there is a crew escape system. Basically it has got fast burning solid motor system which will be operated and the crew will be taken away and then they can land by parachute. So these three systems, launch vehicle, orbit module, then the crew escape system, all the developments are going on very well. But you know, it is a new game and lot of new developments and multiple teams are involved. It is not only ISRO team, there are other organizations like Air Force, Navy, then DRDO and academic institutes, and so many teams are involved. Because for the first time, normally when you take a rocket, we are only playing with the hardware.
Yes.
But here, along with the hardware, there is also a human interface.
Yes.
So it is a little critical thing, and we have to ensure the safety of our people. That is the paramount important. So all the developments are going on well. Now this month we are going to carry out a important experiment. That is the first experiment. We call it as a test vehicle experiment for demonstrating, rather validating crew escape system.
Okay.
What we have done is we have developed a rocket using the truncated version of the liquid Vigas engine, and but it is a total new stage which is developed, and that stage will take to some required conditions in terms of Mach number, in terms of height, altitude it will take, and then a simulation will be carried out as if there is a setback. Then the crew escape system has to really operate and it has to come back safely. And like this, multiple experiments are planned. The first experiment is planned somewhere this month end. We are planning. Date is set to be announced, and we are going to have that first experiment. I am happy to inform that the project is going on well, but then it is a very involved job and it takes some time to complete all these experiments and go for the actual program. In fact, after carrying out the multiple experiments, we are planning to have basically 3 vehicles before the actual vehicle. One we call it as a experimental vehicle, that is the human rated Mark 3 vehicle with some of the orbital module and crew escape system, everything we are going to integrate, and that is planned somewhere in the first quarter of next month to validate the vehicle system and all other systems, aerodynamic characterization, rather validation, and then the crew system and everything we are going to have. Subsequently, there will be 2 vehicles, we call it as G1 and G2 vehicle, and that will be identical to the actual system, not only vehicle plus entire system, actual system, that we are going to have almost 6 months gap each. Then we will study all the results, and once we are convinced things are in order, we will authorize the H1 mission, where our brothers will be taken to safely to the required place, then we will bring them back safely.
Okay, so the immediate target of Gaganyaan is going to be the TVP,
test vehicle experiment.
Okay.
That is the immediate target what we have set. Like that, so many experiments are planned.
Okay, sir. Then I understand that you are also the chairman of the certification board of Gaganyaan, and that is a very crucial role, isn't it? So what are your feelings about this role?
No, this is in fact, the team was working. This is a new role given to me as the chairperson of that board. It's a very challenging job, because this particular board, which consists of members from different centers and different domain expertise, we have to really clear all the systems, rather certify the systems. Let it be the rocket system or the orbital module system or the crew escape system. We have to understand, first of all, we have to put a system to realize the right product in terms of process control, in terms of material selection, in terms of material control, in terms of manufacturing process control, and in terms of controlling the assembly and test procedures, and in terms of carrying out the necessary, ensuring the necessary testing and qualifications, and finally understanding, yes, everything is in order, then the flight hardware realization, that data also will be presented. Then we have to fully ensure the right things are done, and the board is given the responsibility, rather board has got a major responsibility of certifying before authorizing the launch. And it is a multidisciplinary game where the system engineering knowledge is very, very important. Probably considering my last 40 years experience, that is the reason rather this responsibility is given to me and my team. My team, when I meant, it is not LPSC team, it is the ISRO level and team, and a couple of external experts are there, and we have to really see the right thing and we have to clear. It is a very, very crucial role, and I am confident the type of experts what we are having and the type of experience what we are having, we will be in a position to do the right job.
Okay, sir. Now, you are widely known as an expert in the cryogenic propulsion field. Could you tell us some of the intricacies of this cryogenic propulsion?
For the launch vehicle, there are different types of propulsion, chemical propulsion systems. And there is solid propulsion, air storable liquid propulsion, cryogenic, semi-cryogenic, there are different types of propulsion. Now, the performance of the propulsion system is defined by a parameter called specific impulse. Nothing but, in a layman language if I put it, it is nothing but the thrust generated per unit weight flow rate of propellant consumption. This is best for the cryogenic propulsion system. Compared to solid, something around the performance is something around 70% higher.
Okay.
Compared to air storable propulsion, it is something around 50% higher. Compared to semi-cryogenic propulsion, it is 35% higher. And that means that is the best chemical propulsion system what we are having. Here what we use is the propellant with extreme low temperature, liquid hydrogen with minus 253 degrees centigrade and liquid oxygen with minus 183 degrees Celsius is used as the propellant. The ice temperature, our water, normally the water temperature at ambient is something around 35 degrees centigrade, and when you reduce 35 degree, we go to 0 and you get ice, and hydrogen gas will get liquefied, another 253 degree you have to go down.
Okay.
And that means from room temperature something around 283 degree you have to go down and it will be liquefied. And same way oxygen is little better, minus 183 degrees centigrade it will be liquefied. Now, first difficulty is in liquefying these propellant and getting at a low temperature, that is a challenge, first challenge. Second thing is, yes, you liquefy, assume ice is there, simply if you keep, everything will melt.
Yes.
And here we are having such a low temperature. So, whatever we have liquefied, it has to be stored with proper containers. Now, there is second challenge. Third challenge is hydrogen. It is a very, very, very dangerous propellant in the sense, if you do not handle properly, you will end up with explosive nature. Hydrogen oxygen, if it is properly brought, it will burn and it will work as a propellant. If you do not properly handle and in a premixed, if you try to do something, then it will explode. It will generate lot of energy, it will explode. So, we have to extremely handle that case. Next challenge is, such a low temperature, when you bring the propellant, store or bring it in a pipeline or something, you have to have a contaminant free environment, because all the other gases will get solidified. Even water molecule is there, everything will get solidified. So, you have to clean everything, ultra cleanliness is required to handle that propellant. Now, material selection, every material cannot be used. Some of the material undergo ductile to brittle transition, so those things you cannot use. So, you have to select the right material, this is yet another important thing. Now, when the hydrogen oxygen is burning, it generates a temperature of something around 3500 degree centigrade. That is the type of temperature it generates. At that temperature, none of the metal will withstand, everything will melt.
Yeah.
Then what we do is, we have a high conductivity copper shell, and outside we mill channels, and there will be one more shell. Between these two cells we pass hydrogen, which is a very good coolant, and the hydrogen is passed, which keeps the chamber in the cooled condition. Inside the temperature is around 3500 degrees, and the hardware temperature it will not exceed 800 Kelvin. And that means the thermal design is so crucial and so important. Then when it burns, the energy release mechanism, that is another aspect, very very important. Now when to handle the propellant, to pump the propellant from the storage tank into the engine, we need pumping system, we called it turbo pump system. You know, our water pump in the house generally it rotates with a speed of 3000 rpm, but here the hydrogen being a low density, something around 50,000 rpm, the turbo pump system rotates. A pump and a turbine which is driving this pump, it has to rotate at that speed. When you go at that speed 50,000 rpm, you know, challenges associated with bearing, seals, then rotor dynamics, and it is highly challenging. And bringing hydrogen oxygen together, and you have to ignite. Okay. And ignition has to happen once hydrogen oxygen is brought inside. The ignition has to happen within 700 to 800 millisecond. If you miss the ignition, you will not have either ignition, sometime you will end up with the explosion. So that ignitability aspect, that studies is very very crucial. And the storing the hydrogen in the tank, the flight tank, you need to have a set of insulation. We have developed a set of insulation called the polyurethane foam based insulation, and thereby lot of challenges are involved in the development of cryogenic propulsion system, because it is the highest, giving the highest performance, and it is a mandatory requirement for the as a upper stage for our vehicles to give meaningful payload. Now this development, if you take, other than India, only 5 more nations in the world is having this technology. And it was in the year 1990, the Mark II vehicle was configured, and then we were doing, just I joined immediately after my M.Tech in cryogenic engineering from IIT Kharagpur with first rank. Then we were looking for some technology support from other countries, because if you start our own, we know it will take more than 15 years to 20 years. We thought if some support comes from other countries, yes, we will be little fast track mode will develop. And initially we signed one MOU with then USSR, not for giving the design technology, not for getting the design, at least to realize one of their engine and stage through Indian industries. But after some time that program, due to geopolitical reasons, it could not go well. Then it was in the year 1995 we took a decision, we will develop our own cryogenic stage, almost configuration, and this was identical to the Russian version of the cryo stage, which was initially used for the initial Mark III flights. We procured some of the stages, and the indigenous development started in the year 1995, and it took us almost close to 20 years, 19 years to complete the development, which includes hardware realization, material development, then establishing infrastructure for testing, and completing the testing and qualification, and go for the flight. And it was in the year 2010 we went for the first flight, but we had a small setback. Then we had to discuss, and then again lot of experiments were carried out, including high altitude test of the engine. And then in 2014 we had the first successful launch of GSLV, the D5 vehicle with our indigenous cryogenic upper stage. This is one version. Second thing is, when it comes to Mark III vehicle, LVM3 vehicle, we are having upper stage as the cryogenic stage, which is totally different from the Mark II vehicle. In terms of, for example, if I tell Mark II vehicle, the thrust of the engine is 7.5 ton. Here the thrust is 20 ton, okay, and there the propellant loading is something around 12.8 ton. Here the propellant loading is something around 28 tons. There it is 12.8 ton, here it is 28 tons. So that is the type of things. And then this is a total indigenous effort. We started from scratch, then we started the development, and of course there were a couple of project directors, initially they were working, and towards the last phase of 6 to 7 years, I was given the responsibility as the project director. Also simultaneously I was also leading as the deputy director the development team, because one is the development team, another one is the project team. Together we have to work together, and we completed all the developments. In fact, I want to say totally before the flight 199 experiments were carried out, and I am happy to report that out of 199 except one setback, everything was successful in the first attempt. Then we went ahead with the flight. The first flight was in 2017. In fact, I still remember when I made the final presentation, we told this is the 200th experiment, only one setback, this will be perfectly successful, and it was in the maiden attempt itself, it was a grand successful mission of GSLV LVM3 D1 with the indigenous C25 stage. And today we are a proud nation, proud ISRO, having two cryogenic propulsion systems which was at one point of time denied to Indians. And with our hard work, smart work and dedication, we have developed and we have joined the elite group of only 5 more nations which are having this technology.
Sir, you started your career in the solid propulsion group, and now you are involved in the propulsion activities, all the propulsion activities of launch vehicles and also satellites. So how did you groom yourself to be a rocket propulsion expert?
It was in the year 1984, 1st February, I joined ISRO in the Vikram Sarabhai Space Center, and I was given an opportunity to work in the composites group, which is currently in Batturkau, and the responsibility was related to the solid propulsion area, mainly ablative nozzle systems for Rohini sounding rockets and ASLV. So I was working in that area for almost 4.5 years and contributed for 2 ASLV vehicles, and one DIAC program with the DRDO, a nozzle was also delivered for that. After that 4.5 years of initial period, I went for my M.Tech in cryogenic engineering and studied in IIT Kharagpur and passed out with first rank, and also did a thesis work in M.Tech related to a flow control device development. Then subsequently did my PhD in IIT Kharagpur in the again aerospace engineering department, working on the cryogenic rocket engine control. So with that in background, I was given the opportunity, rather working in liquid propulsion system center. Initially worked in the experimental phase of cryogenic propulsion, then the cryogenic upper stage development for the Mark II vehicle, then Mark III vehicle. Of course, as I told, I was so blessed to be the project director and development chief as deputy director and worked in that area. Then when I was elevated as the associate director, I had the opportunity to overview the activities of the air storable propulsion system for launch vehicles. Then subsequently, when I became director almost 6 years back, January 2018, the entire activities including satellite propulsion was with me. Thereby, I had the opportunity to contribute solid air storable liquid, cryogenic, then the satellite propulsion, and currently we are working on the advanced propulsion systems like LOX methane and the electric propulsion for satellites, and of course we have also initiated something on nuclear propulsion related activities. So lot of all propulsion activities I had the opportunity to work. Now with respect to cryogenic propulsion, I want to tell one specific contribution. My M.Tech thesis, where we have developed a flow control device called cavitative injury, and PhD thesis where we have developed a mathematical modeling of the cryogenic rocket engine, both found direct application, both were employed directly for the development of both Mark II vehicle cryogenic stage and C25 cryogenic stage of LVM3 vehicle, which has been successfully employed for the recent even Chandrayaan 3 mission and which is going to be used for the Gaganyaan program also. So this is a great opportunity professionally for somebody, the true thesis work directly finding a application. Now, with all this background, right now I am having multiple roles like MRR chairman, Mission Readiness Review Committee chairman, then the Space Transportation Project Management Council chairman to review the multiple activities. With all this background, I will not say I have become an expert in overall propulsion systems of launch vehicle and spacecraft. It is the organization which has made me as a overall propulsion expert of both launch vehicles and cryogenics. It is the organization, repeat, it is the organization ISRO which has made me as a expert in the launch vehicle and satellite propulsion systems, including the advanced propulsion systems like electric propulsion, nuclear propulsion, then the LOX methane propulsion system, and liquid oxygen and kerosene propulsion system. All propulsion systems, the organization has made me to contribute as an expert.
Okay, sir. And what is your assessment of ISRO's roadmap regarding the future space transportation systems, and how is it going to evolve in the next 20 years?
Say in 1980, we had the first SLV-3 launch and we placed a 40 kg spacecraft in the orbit. From that, we have come a long way. Today, our Mark 3 vehicle capability is something around 8500 kg we can place in the low Earth orbit. Now, currently, we are trying to improve the Mark 3 payload capability. The Mark 3 vehicle, LVM-3 vehicle, the cryogenic upper stage, we want to improve the performance by taking more propellant loading with high thrust engine. That development is going on. We call it as a C32 project, that is going on. And the core liquid stage, which uses the air storable propellant, that system we want to replace with a liquid oxygen kerosene based, a 200-ton thrust powered the semi-cryogenic stage. With this, the Mark 3 payload will be improved 25% more. So, this is one of the activities. Second activity is, we want to enhance the payload capability from the current 8.5 ton to LEO to something around 17 ton, 2 times. And that cannot be done by simply improving the performance. For that, we are planning to develop a new generation launch vehicle. So, the configuration studies are right now underway, and which will be powered by a liquid oxygen methane based rocket engine, and that engine development just we have initiated. And the first stage there may be 11 engines we will be using, second stage will be a 3 engine, third stage may be a single engine, and so this is another vehicle development in the space transportation system. Now, these are all called expendable launch vehicles. Whatever till today we are having is expendable launch vehicle. Expendable launch vehicle means one shot operation. Now, to reduce the cost to access to space, cost for access to space, multiple time you have to use the rocket engines or rocket systems. So, we call it as the reusable systems, and now couple of experiments are carried out, including recently this year April we had a LEX experiment. There was a body which was landing autonomous way, and using all this expertise, we are planning to develop the reusable launch vehicle system and induct. Reusable multiple times you can use. So, the propulsion system also has to be qualified, structure everything has to be designed to meet that requirement, but advantage is you can use 15 times, 20 times you can reuse, like that US whatever they are doing. So, this is one of the development which is going on. And another thing is, currently we have invested heavily on air breathing propulsion systems. Basically, we have done the technology demonstration. All these things has to be brought to a logical conclusion and induct into the space transportation system. So, this is one of the area we are working. Now, in terms of power system, for example, now we are having lithium ion battery, and we are also developing fuel cell, hydrogen oxygen based fuel cell. So, this type of technologies which has to be brought inside, new technologies. Another area is manufacturing. Materials and manufacturing is key for any space transportation system. There also we are concentrating on the new manufacturing process like additive manufacturing, flow forming technology. So, this type of technology also we are looking for. Thereby, I foresee like this. Today our capability of the vehicle is something around 8,500 kg to low Earth orbit. Maybe in 7 to 10 years from now, we will have a capability double of this.
Okay.
And somewhere in 2040, 2045, with new technology whatever we are thinking of developing, probably this capability will become very huge, maybe more than 100 tons plus, but that is yet to be discussed and debated, but this is what is my thinking, because the other countries their capability of that order, and then that is the type of capability what we are trying to build maybe in another 20-25 years. And to meet that, host of technologies has to be developed. So, we are going to concentrate on those technologies to meet this type of huge activities.
Okay, sir. The design and development of a spacecraft was also an integral part of India's space journey. How well have we done in this arena?
No, spacecraft really we have done extremely well. And our first spacecraft was Aryabhatta with the support of USSR. We realized in the year 1975. And then the SLV satellite, whatever we used was a 40 kg mass satellite. And from that complete beginning of Aryabhatta, we have realized some experimental satellites for the communication, for remote sensing, and to our credit today, we have designed, realized and flown something around 125 spacecrafts of different types. Earth observation satellites, communication satellites, then navigation satellites and star satellites for strategic application. We have realized 125 types. Now, if I put our capability today, the SLV-3 1980 we realized a 40 kg satellite. From that we have realized the heaviest satellite realized is GSAT-11 communication satellite, approximately 6000 kg is the satellite mass. So, 40 kg to 6000 kg. And in terms of the power, from 20 kilowatt to 60 kilowatt is the type of power we have realized. And in terms of payloads, for example, take the Earth observation payloads. Initial satellite, the resolution of the camera used to be 1 kilometer, and we brought down to 76 meter, 32 meter. Today, we are having best optical cameras in the world. For example, take Chandrayaan-3, we are having a on orbit high resolution camera, 30 centimeter is the resolution of that camera. And we are having other cameras, if I am correct in the RISAT program, 28 centimeter. These are all international standard cameras. So, thereby the payload we have moved a long way, and these optical payloads will be used only for taking the photograph when the right weather or other clouds are not there. Whenever rain or clouds are there, these optical payloads cannot take any photographs. And we have wetted our hands with microwave remote sensing payloads. All weather condition you can get the photographs. Okay. So, there we have succeeded, and right now we are we are realizing so many things, and we have inducted. Now, communication payload and another huge improvements, and today the communication has got revolutionized in the country because of those payloads. Then we are having navigation systems, navigation satellite. We are having a host of navigation satellite we have launched, and using that, the position accuracy is less than 10 meter we can get the position accuracy. Okay. And today if you see application of that navigation thing, all our trains, we are having something around 8,000 plus trains in the country, and already 2,800 trains we are tracking real time. Okay. And so many boats we are tracking real time, and the vehicles we are tracking, and it is going to be used for strategic application, it is going to be used for our airport authority, and so much. Once you are getting such a signal, the position accuracy is so good, and we are having. And in the area of satellite, from 1975 taking support from other country, we realized the first satellite. And today, one thing I want to tell to our credit, 125 satellites we have realized and launched, and one of the satellite I should mention, our Honorable Prime Minister, he gave a guideline to us. We have conceived, realized and launched the South Asian regional satellite, and we have donated to SAR countries. Okay. So, it is a very big journey, in terms of satellite technology, in terms of payloads, in terms of this one, we have come a long way. And today we are having capability to develop and realize any types of satellites. Satellites for ocean application, satellites for strategic application, satellites for communication purpose, satellite for television broadcast, what not. So, all the capabilities we have built over 5 decades.
Sir, could you explain some of the specific as well as general applications of satellite technology?
Say basically our space program is meant for bringing the application of space technology to the common man of this country.
Okay.
And we have served this country in a big way. For example, earth observation, and these satellites are used for ensuring food security by monitoring the crops forecasting, and water security by taking the underwater groundwater storage and other conditions, and then the total resource management like monitoring the forest, monitoring the ocean, and so many resource managements, and cartography, town planning, so many things it has done. And one of the applications, for example, take India is having 7,500 kilometers of seashore, and so many people are involved in fishing activities. And we monitor the potential fishery zones, and we inform our colleagues where they will get fish. And through that application, how much profit we are getting? 37,000 crore profit per year we are getting, and ISRO budget is only 14,000 crore, and that is what. Another thing is you take disaster warning and management. Today we are having the satellites which really give advanced information about the flood or landslide or lightning related aspects or tsunami, what not. And through that we are in a position to inform our citizens and save them. There was a time we used to any natural disaster we use our citizens, but today that is not the case. We are in a position to inform. This is worthless to get that type of benefit. Another thing is communication. Communication, we have made so many communication satellites and we have made revolution. And navigation, as I told, position accuracy, and then there was a time even our fishermen, when they go inside, or why fishermen, the people who are inside sea, they do not know the exact location. Are they crossing the Indian border? They were not aware. But today we are having apps where the signals are coming and they are informed. They are crossing, what is the current location, where is the international border, everything is informed. Now you take the television broadcasting. There was a time where was the TV channels? When I joined ISRO itself, hardly 1 or 2 channels, but today multiple channels, how everything has come. And telemedicine, and television broadcasting, and tele-education. Today of course internet has come. Before that there was a time tele-education played a very, very crucial role. And telemedicine is very, very important application, and you can from remote place they can consult the doctors and they can give the treatment, and like that I will say there are something around 40-50 applications. And then our country is a vast country, the safety of the human being and the strategic application, we have to monitor the border, what is happening, and so every area I will tell we have done great job. But then lot more thing can be done, lot more has to be done. Today out of 125 satellites, around 50 satellites are in the orbit, but the need for satellites and other things are huge. 50 years back people were not aware of the benefit of space to the common man, but today everybody is aware. To understand the benefit of the spacecraft, one has to do one thing: evening time, just 1 hour switch off all the spacecrafts. No ATM will work, no television will happen, and you will not get proper signal for your telephone connection, and everything, life will come to a standstill. That is the place it comes, and then the border security, everything, it will be really a difficult process without the satellites. Really the space has done great service to the common man of this country during the last 5 decades through the satellite system.
Sir, can you comment on the space sector reform rolled out by the government of India?
See, if you see the demand for the country in terms of satellites are huge. Whatever we have done is yes good, but then lot more thing is required. Now, if you run with the present mode of only realizing through the ISRO system, we are not going to meet the requirement. So, the credit goes to Honorable Prime Minister of India Modi ji. His vision, he felt that the space sector, space activity should be done not only by ISRO, also should be done by private sector and startups, which will bring lot of benefit in a fast track mode to the common man of this country. Now, he is a man with great vision. I will tell you, our Prime Minister is a person with great vision. He understands how the advanced technology can be used effectively for the common man. So, he strongly feels, and we also believe in that lot of things has to be done, and that is why the space sector reform is brought inside. Thereby, whatever facility we have built, ISRO is going to enable private industries to carry out the space activities in terms of building launch vehicles, in terms of building satellites, in terms of ensuring its successful launch. Not only that, another important area is, today we are having so much wealth of satellite data and utilizing for the common man. You have to do lot of processing, lot of algorithm development and taking to common man. These things are possible by enabling lot of stakeholders into the system, and that is why the space sector reform has come and new space policies rolled out, and ISRO is going to handhold and enable startups and private people to carry out space activities. And one major advantage is when you roll out, for example, our PSLV already we are giving out to industries, they are going to manufacture. By this process, the ISRO team will be in a position to concentrate on advanced R&D activities. So, whatever space sector reform, whatever done is excellent, and it is going to bring lot of benefit. Maybe downstream I am seeing another 10 years, if you see, it will be bringing lot of benefits out of this.
Okay, sir. ISRO's space journey had a humble beginning, because I have seen rocket parts being transported on bicycle and satellite transported on bullock cart. Which are the areas in which ISRO has excelled in?
Very nice question. Yes, we had the humble beginning of space program in the year 1962, and 1967 we had our indigenous tiny rocket taking place. From that we have come a long way. To our credit, till today we have launched something around 3,500 plus Rohini sounding rockets, developed 6 generations of launch vehicles, starting from SLV to the recent SSLV, and 91 launch vehicles we have realized and successfully accomplished launch vehicle missions, and 125 satellites we have realized. And not only that, 1975 we realized a satellite using others technology, and the satellite was launched by other country. And today, to our credit, something around 431 satellites of 34 countries we have launched from Indian soil. Now, when you ask this growth from the bicycle and bullock cart era, today when I look at, really we have gone to a phenomenal growth. Not only that, I will tell you one point. 1967 when we had a 7 kg rocket lifting off, you should understand where the world was standing. 1961 Yuri Gagarin has gone to space and he has come back. It was in the year 1969 when I was in the first standard, sitting on the floor along with a couple of my classmates. Our teachers came and announced, yes, today man has landed on the moon. During that time frame, our space program started with a small tiny rocket launch in 1967. That was the indigenous first rocket. From that, today when you look at our growth, it is phenomenal. Only we are doing service to the common man. A couple of places I must mention. Take Chandrayaan 1 spacecraft, and that is the first spacecraft of India which found water molecules on the moon and made every Indians proud. And through that satellite we also put our tricolor on the moon surface through a moon impact probe. Now, you take Chandrayaan 2, even though we could not accomplish the soft landing, we are having a orbiter. Originally we designed for 1 year, but later the life really became because of our smart work 7 years. Right now it is rotating in the moon area, 100 kilometer it is rotating and sending thousands of photographs, and the resolution of that camera is 30 centimeter. That is the best in the world and the best output we have got. Thereby the product is best in the world. Take Chandrayaan 3, it has landed on the South Pole and made India as the proud only nation which has landed in the South Pole. And take the multiple satellite launches. Actually, at one point of time, the Russians, they had accomplished 37 satellites launched in a single mission, and we put a target, we launched more than 100. And launching is very easy, but you have to place in the right orbit, and it was accomplished perfectly, and India became the first country which has successfully accomplished more than 100 spacecraft, rather correct number is 104 spacecraft in a single mission. And when it comes to the cryogenic technology, it was a technology denied to us, and without that there cannot be any proper space program. And today, to our credit, with the Indian education system, with the Indian scientists, we have developed 2 cryogenic stages. Of course, we have taken little more time for the Mark II cryogenic stage, but C-25 stage we have taken this one, and today, to our credit, we are having 2 cryogenic propulsion systems. And among that, the C-25 cryogenic stage, if you see, we are having world records. For example, from the time of successful testing of the engine to the flight, we have taken only 28 months against other countries' lowest time of 42 months. And you take a stage hot test of C-25 stage. Now, generally, the full tank, engine, everything put together before launching, we do a stage level test. Every country has taken almost 8 to 12 months after realizing, taking to test stand. They do multiple experiments, they have done. But we took one managerial calculated risk. We will not do any experiments, straight away we will do the hot test. That is not just like that done. We so many theoretical studies were done, and that was decided. India is the only country which successfully accomplished in 34 days this stage hot test, and no other country has done, no other country is going to take that risk and going to do that also. And our SRE program, Space Recovery Experiment, and successfully we brought back.
Yes.
And that product, when it came, it was brand new, as if it has not seen the space. That is what we saw. Now, you take our air breathing activity, where we have to ignite under high Mach number conditions. In the first attempt itself we accomplished, and thereby in multiple places today India stand on first place, and throughout the world they respect us. I think our former President Abdul Kalam used to say, strength only respects strength. Yes. There was a time we were weak, nobody was minding us. Today we are a technology leader in this area. Of course, lot more thing has to be done, and today really we are well respected across the globe for our contribution towards the ISRO space program and achieving some of the missions in the right time and with the top ranking. Another important thing I have to tell, our Mars orbit mission, we have to take a spacecraft to red planet, and we have to travel 68 crore kilometers, and we have accomplished in the first attempt, and India is the only country which has succeeded Mars orbiter mission in the first attempt. Even no other developed country has succeeded in the first attempt. And not only that, if you take the total money, amount spent, rather cost spent for that mission, and if you calculate the cost per kilometer travelled, I think our Honorable Prime Minister used to say that is lower than the money what we are paying for auto fare. So, that is a low cost mission we have accomplished. Thereby, today the Indians can be proud that we are second to none in the space area. There are places we are top ranking, even though we started with a humble beginning, behind 60 years we are behind, but today lot of places we have compensated, and our flag is flying very high in the international arena.
So, what is your message to the youngsters of this country?
I strongly believe the youngsters should have got a feeling, they should believe within them. We should believe that yes, we can accomplish. For example, take Chandrayaan 3 as a mission. We strongly believed that we will be in a position to successfully accomplish. So, one should have got a self confidence and self motivation. Of course, hard work, there is no substitute for hard work. Along with hard work, one need to have smart work also. And one should not be afraid of failures. Yes, failures are after all the stepping stone for success. For example, take Chandrayaan 2, we had a setback and we cannot lose our heart. Yes, setback is setback, but you have to learn the lesson out of it and we have made it successful. So, do not worry about failure. When you work, there will be failures and you use it as an opportunity to succeed. Always the youngsters, you should grow as a good human being and you should respect elders, respect teachers, and then you grow. And you know, one should have, there are two types of education. One is called intellectual education, which touches the brain. Another one is called value based education, which touches the heart. A person without value based education, only intellectual based education is no use. So, one should have acquired both the things. And of course, the overall personality development, not only academics, you have to have overall personality development. Once you have that development, you will worry about your surrounding, you will worry about our nation and what not. And another important thing is, when you come up in the ladder, always you should believe and you should practice that the organization, the family, the country is above individuals. Individuals are nothing, because we strongly believe ours is a team work organization. Individuals are nothing. As a individual director, what I can do? So, individuals are nothing, organization is above individuals. Then a open culture, a frank and open culture, that is important. Let me quote a statement from the Wings of Fire, the autobiography of our former people's president, Dr. APJ Abdul Kalam. The total, I quote, the total commitment is the pivotal quality for those who wants to reach the height of their profession. I unquote. Dear friends, yes, I strongly believe in that statement, and one should have got continuous education and value your parents, respect your elders and contribute for making this country as a developed country when we celebrate 100 years of independence in the year 2047. Thank you viewers. Jai Hind.
Thank you, sir. Thank you for the vivid narration of ISRO's exciting space journey. Thank you for your time.
Thank you, Renju.
Thank you.
It's a great time. Thank you.